Thank you. Yeah, thank you very much, Marcus. So what I'm going to present is the first steps that we are doing in NOMAD and in FAIRmat to represent solar cells in the infrastructure that we typically use. And here is work of a lot of people, like either in ideas or in commits, and there's like the whole FAIRmat team involved in it. So I wanted to start showing this diagram in here. It represents the conversion efficiency evolution of novel solar cell technologies over the years. So it represents the efficiency evolution development in there. And if you are very rough, like fitting this like into these like blue lines in there, what you actually can like infer is that it really takes like at least like 30 years to bring like a new technology to a 20% level of efficiency, which is when they can have a chance to even become commercially competitive. There's one exception here, which is the halide perovskite, which is this red line in here, which is out of the norm, is because of many peculiarities that we will not like cover in this, but just to show you, it takes like decades to reach this point. And the reason is behind the classical way that we do research solar cells. So I'm an experimentalist, and so what we typically do is like we have the literature, which is like really large, and then we read the literature, and then based on what we read and what we share with our colleagues, then we synthesize these main materials that compose the technology of the solar cell. And then when we like develop these materials further, we measure them, we characterize them. When we are happy with the properties of these materials, then we need to implement them into a full solar cell device. And when we are able to make this device like somehow works, then we write a paper, we publish, and we feed again the literature. And the problem is like in all of these arrows, they are like highly inefficient. It's slow, and this like doesn't allow us like to accelerate this process. And I'm going to like try to navigate through these arrows and see what we can do with data management to try to improve. So first of all, like the literature part. So if you look, for example, for one of the technologies, this perovskite solar cell things, and you go to Scopus and write perovskite solar, this is a technology that is like 12 years old or like not even like 10 years old. You get 27,000 papers already. So this is like impossible to digest. Like if you are like a new poor PhD student that want to like start like making solar cells and want to have like a grasp of the literature, this is no way that you can like navigate this. So there are some other like sources of information that can like help you to digest the literature in solar cells. This is very popular one is the NREL chart by the National Renewable Energy Laboratory of the US. If you see solar cell talks and conferences, you're very likely to see this chart. It appears everywhere. It used to be totally analog, but now I think you have an Excel table where you can extract the efficiency associated to a technology or something like this. But yeah, great. And then there are review papers which contain efficiency tables. And these efficiency tables are like, for example, if there's a review paper about a solar cell technology, you have like a table in a PDF which contains some device properties that is again like totally analog, and you cannot do any data with this, but at least it helps you to navigate the literature somehow. And then there are starting to emerge some databases, and here I like two examples. One is the Perovskite database project, which I will talk like in detail now in the following slides. And then there's another one which is called the Emerging PV, which is hosted at one of our partners in Erlangen. And then in there, you can have like interactive plots in there that it helps you like to find a data point that it might be interesting for your technology. And then you can reach the publication with this data point has been in there. But still, in the case of the Emerging PV, it doesn't really allow you to work with the data. I think the Perovskite database project is like something very peculiar, and I will try to give some details about this. So this got published last year, and it was led mainly by two researchers at the Helmholtz Center in Berlin, Jesper Jacobson and Eva Unger, which is a collaborator of FAIRmat. And how this worked, it was a massive crowd effort where they put like 100 authors together, and they manually digitized information about 42,000 devices out of 16,000 publications. And how this worked, it was like they defined 400 metadata items in a template Excel file, and every author had to go through 200 papers and collect this data and put it in the right place in the Excel file. And they created like an amazing database for this, and it contains synthesis information, stability information, something very, very special. So it's really a pioneering project in the field, and it's been a catalyst for data-driven projects in the community. And one example is us in here. So the database, just to put like some red points, it doesn't contain array. It's all arrays. It's all scalars, and the raw data of the measurements are obviously not in there because it's created from the literature. And what we are facing now is that like it seems to be difficult to keep updating these new entries, and the reason for it is like because like these manual curation campaigns are not very sustainable. So we need to find a way to implement this data collection much more organically, like through ELNs and so on. So this is where like NOMAD comes in. I'm going to show the visions and the first steps that we're taking in the solar cells. So first we want to create like we created a common home for solar cell data. We'll go into details in there, like regardless where the data comes from, that you find like a place where you can search for it. Then we implemented the Perovskite solar cell database that you can visualize with the NOMAD tools, and we augmented this data set somehow. Then we are building examples on how you can digitize these efficiency tables that it comes like typically in PDFs in the publication, so you can also like search for their stuff. And then we're building examples for ELNs, electronic laboratory notebooks, specifically for solar cells in the context of the NOMAD Oasis that has been presented before. So with a common place for solar cell data, so what I mean with this thing is that whether you have like a paper with an efficiency table like this, that like it has parameters about solar cell performance, efficiency, open circuit voltage, JC, device architecture, and so it has like a very basic like a schema behind, or you have large databases containing data like the Perovskite database, or your laboratory data that you like register with an electronic laboratory notebook, you can find a place like now in NOMAD where you will be able to search for this stuff. So if you go to the beta version of NOMAD and you go to Explore, you find like new tabs in there, and then one of the tabs that it is in there is the solar cells tab. And when you click in there, what you find is an interface where you can create dashboards to explore stuff. So for example, you can click on the chemistry of the absorber layer of the solar cell, and then you have like a specific like, parameters of the solar cells in here that you can filter. You can further filter by like bang-up values, or even by the layers of your solar cell stack. And when you are happy with what you do, you can navigate deeper into the entries and find the additional information that is like synthesis or whatever else you have registered in there. So the Perovskite database can be, so the data in the Perovskite database can be explored already in there. So if you go to the beta version, you can look at it. By implementing the Perovskite database in NOMAD, we are not just like copying the data, we also are adapting the data that we make it more interoperable. So for example, like now, if you look for a cesium lead iodide in the overall like NOMAD, you will get hits of DFT calculations based on cesium lead iodide, but you will get like solar cells also built with this composition of this absorber. But then now it's like this data curation, how we're going to manage this data. So what we're creating is also within the context of NOMAD Oasis, like example ELNs, where you can just build your schemas, and you can be very flexible for that because it's like based on base classes that we are developing for solar cells. Within these schemas, you can have forms that allow you to register data manually, but also to include your experimental data. For example, this is an external quantum efficiency spectrum that you typically find in many publications. It has like a unit system to control that everything gets like uniform. And this is what we want to like bring to the labs now. So these within these ELNs, you can also like use them to augment the data and just like bring an example in here. So this external quantum efficiency spectrum is like two arrays, intensity versus wavelength. So it represents how efficient the solar cell is in like generating photocurrent for a given wavelength. And you can like in NOMAD process this with some methods that we have developed specifically for this measurement. And yeah, then it gets processed and it augments the data set. Like it extracts the bang gap with state-of-the-art algorithms published in the literature. It fits like an URBAC tail to the exponential thing. And like this, by deploying the same module in several labs, we can have consistent analysis in all of the external quantum efficiency data that gets like in all the labs I would like to work with our infrastructure. But now this like help us like to cover the literature part, like what can you do like to develop a little bit faster the materials. And I guess the trends are like you can do combinatorial synthesis. This is parallelized like to do more in less time, in which case you need like some data management tools to help you navigate this data. You can do high throughput characterization. So if you like measure more, you need also like data management tool that allows you to analyze this data a little bit better. There are even starting to be examples of autonomous labs with like robotics that this will necessarily need to have like a data management tool behind this. And then like you want to have like AI to give you an extra boost to it. So you need to have your data AI ready for that. So by making your like data fair, like for example with our platform, then machine learning becomes much more accessible. So for example, this is a representation of one formula, experimental formula typically used in high efficiency perovskite solar cells. FA stands for formamidinium, and then MA for methylammonium. And what you end up like having is very complex stoichiometrics where you mix different cations in the same Wyckoff position. And like if you convert like this to a real formula that you can apply in machine learning of state-of-the-art algorithms, then it looks like this. And if you wanted to calculate, for example, the bang gap of this stoichiometry with a DFT calculation, you will need like a unit cell that it will be massive and it will become like a very expensive process to do. But because we have a lot of data in this context, then we can train like machine learning models that they come like just packaged very well. And one example is here is this CrabNet developed at Utah University at the group of Taylor Sparks. And what you do is like in 3 lines of codes, you can train with this data a model, and then you can predict these complex stoichiometries in halide perovskites like within 70 millieV. And it allows you to do already the very most simple example. It allows you to do things that you couldn't do before. But then, yeah, we reach the point where we need to integrate our materials into a device. So this is very slow too, because yeah, we have we develop our material, we measure it, okay, we reach to the point where it's really ideal properties, so we think that it's going to be, and now we need to select which layers we want to build the device with. And what it typically happens is that you use the layers that somebody in the lab has been using for another parent material or something like this. So yeah, or maybe you are like a really good chemist and have some educated guess on and think what it could be work fine. Yeah. But these educated guesses have the limits. So what I did an API call to the NOMAD, to the Perovskite database, and I extracted all the charge transport layers that have been used in the Perovskite database to check which combinations have been used in there. And yeah, it looks like this graphing here is the only way that I can show you all of these possible combinations in here. And I was even surprised of how much it has been tested. So like every point in this graph, it represents a charge transport layer that has being used, and every line it represents the connection that has been done with one. So if you do some really basic topography analysis of this network graph, so you end up that you have like more than 2,600 charge transport layers used, and in combination like more than 3,000 possibilities. And even if you're like a really good chemist, you cannot have the chemical intuition like to navigate you through all these possibilities. So like to really accelerate the device implementation, we also need to deploy like new tools that help us like in making these decisions and visualize it. So what you can do in NOMAD now is like if you go to the Explore at least, so you can somehow select one of the layers that you have in there, and you get like some statistics now. So let's say that I want to look at solar cells that have used C60, and then it automatically like gives you like a search of like which have been the most likely combinations for solar cell whole transport layers that have been used, and you can look at further statistics on performance of devices and so on. Okay, so I think I'm slowly concluding with this. Yeah, we don't have 30 years to develop new materials for solar cells, and we want to have a lot of like new materials that they are like cheaper, they are less toxic, they are earth abundant, and even at some point you even want to have them that they get mined and fabricated in regions which might not have geopolitical problems too, so who knows, but we need possibilities. But we don't have 30 years to afford the development. The only feasible way as an experimentalist that I see we can accelerate this is through data management activities and fair data management activities. And we hope that like this, we can convert this into an efficient workflow. I don't think that like engaging these activities, we should only do it because funding agencies are asking us to do it or because we want to be more organized, but I would like to encourage scientists to do it because it will enable like a new way also to do research that we couldn't do before without these tools. So how we want to start next year is to try and to like these like tiny examples that we've been building for ELNs and so on, like to really bring it like to the real deployment and the production labs. And we have the luck to have like cross projects that are like very interested into this, and we have very like big collaborators interested in this, and we are going to try to start like piloting our infrastructure in some big labs of the Helmholtz Association, like for example at the HCP, at KIT, and maybe also in Erlangen. So yeah, thank you very much.